Okay, so today with Year 11's Unit 1, we'll cover 9F similarities and 9G. Um, we'll be using the similarities from 9F, but we'll apply that to the proofing. Just again with the proofing, you need to make sure you do the steps in the right order. You make the starting assumption, you use the geometric properties of your starting assumption, and you do sort of working out in logical order. It's important that you follow the same way the structure as you do your writing. You go from the left to the right and downwards. You don't start jumping around all over your page. It becomes really messy. Okay? So with the similarities, they are the properties you're going to be using to um, to show that two shapes are similar. The application you're going to be using is with triangles. It's not something new. You should have been done that in maybe year 9 or year 10 with similar triangles. Now, the properties of similar triangles is they all gonna have the same angles, okay? And when you do the ratio of the corresponding length, it will be equal to the same amount to that we call a scale factor. So, for example, if you have two triangles um, that are similar and one is double the size mean let's say the length, each length will be respectively larger, a double. Then what's going to happen is if you do the ratio of the respective length, it will be equal to 2. And again, all the angles will be equal. Okay, very useful application with vectors, which is linked to geometry. So the main three ways to find for scaling triangles is using these three properties using acronyms. So triple A's will be two angles of one triangle are equal to the two angles of the other triangle, meaning that when you know the two angles, because all the three angles add up to 180, if you know two, the third one is implied. So it's three angles for a triangle. You can narrow it down to two. Okay. SAS is side angle side. So two sides will need to be have an equal ratio for the two corresponding sides, and the angle in between the two sides will have to be equal. Okay. And triple S is when you do the ratio of all the three corresponding sides, it will be equal to the same ratio to the same scale factor. Okay. Um, the fourth one is just in a situation when you have a particular triangle that is right angle. So in that case, if you do the ratio of the hypotenuse, um, and the you're gonna need another side. Okay, so hang on. So the R stand for, you need to have one right angle. The H is the ratio of the hypotenuse, and you need one of the other two remaining side. The ratio needs to be the same as well. Okay. All right. So you will have that shape. So those two parallel lines uh, inside. So you will have various dimension, and what you need to do is to find the value of x. The way you start it is again is you need to look at identify your similar triangles. Here a quick trick to find out is that corner is actually a common vertex of both triangles. From that you need to extrapolate which triangles you're going to look at to determine if they are similar, and once you have proven that they are similar, you can use either the equality of the angles or you can use the ratios of the sides. Okay. So let me go back. Obviously, I don't have the working out. So here you would look at the triangle A, B, C, and A, X, Y. Okay. And I'm gonna use my lovely overhead cam if I can make it work. Yes. Let me see if I can do that. way you would do your proofing, you look at your triangle ABC and triangle AXY. Okay, so the first thing is you look at, and obviously you can't see the figure, so let me move that down a bit. I'll move that up after I don't need the shape anymore, the drawing. So here you will look at your angle. So you know your angle BAC is equal to your angle XAY. So that's from the drawing. Okay, there's no proofing, it's just, you know that AB, you look at the point A, B, and X are on the same line, A, C, Y on the same line, so I can go from A to C as well as A to Y. So hence I can use those equality of the angles. Then the other property you're going to be using is those two lines are parallel. So any line that is cutting across those parallel lines is a transversal line, and you have properties that will be useful. So let me use that. Going back to here, I can use a pen. Yeah. So here, two parallel lines, I can see that angle is actually the same as this one. They are called corresponding angles. So being corresponding, you need to specify that in your working out. So I'm going to write angle ABC is equal to angle AXY in the same order, and that is because they are corresponding. Okay, so now I have two angles in the triangles. Then I can say this is enough for the property triple A, and I can conclude that those two triangles are similar. Okay, now knowing that they are similar, hang on, the chat is flashing. Are you asking something? Because parallel. So I use the two parallel lines. I identify two angles from the two respective triangles to be equal. So those two angles are corresponding angle, okay, and they are equal. So that comes from a combination of the parallel lines and that line ABX being transversal. Okay. All right. So now to find the value of x, yes, Louis, are you typing something or? Okay, so with the ratio of the lengths, you see on this side, it's going to be equal. So what I'm going to do is the ratio of the larger triangle, so it's AY. So I can write AY divided by AC. So that's the ratio between the larger by the smaller triangle, a side of the triangles. It's going to be equal to the longer side, which is AX. So on that side here, divided by AB. Okay, so I substitute that, that's 3 to, that's 5.5 divided by 3 is equal to, the AX is X plus 6 divided by X. Okay?
Sir, could you move it up? I can't see it.
Like that?
Thank you.
Okay. So now, what I do is you can do a cross product. So that gives you 5.5 x equals 3 bracket x plus 6. You expand and I regroup the like terms. So that's 5.5 minus less 2.5x equals 18. That's 5 over 2. 36 over 5. Okay? Hopefully.
Yes.
Okay. Next example. It's a little bit of a language here, and again, every time you have a worded question, you need to come up with the correct drawing. Okay. So let me move this out of the way because I don't think you can see. So you move that. So here you have a triangle ABC, the altitude AE. Hang on. Okay, so the way you would do that, do I draw that here? I can use a new piece of paper. So when you draw your triangle, I'm trying to make a scaling triangle, nothing special. I don't want to make it, it looks like a right angle, too late. Okay, so that's A, B, C. When it's specified the altitude, can I do this? Actually, the drawing is already there anyway, but I'm in the wrong slide. Okay, never mind. I'll continue. So with this one, the altitude AE, it means that you start from A, and the altitude means it's going to be a line inside a triangle that's going to be intersecting the opposite side at a right angle. So you try to do something like that, and that's going to be a right angle here, and that point is what we call E. That's how you build up your altitudes inside a triangle. Okay? BF, it's from B, it's going to intersect AC at F. Now that line needs to be perpendicular here, and that's your F. And that's how you determine the point E and F. Okay? Now by constructing this, what you're going to end up is you're going to have triangles that are going to have, you're going to have two right angle triangles, and they're going to have an angle that is in common here. So with that triangle, the intersection, I'm going to call it H. So AHF and BHE. By the next step, I'll show you that they're actually going to be similar. Hang on, let me read that what Louis is writing. What if okay, if on the side of the, in a particular situation when you have a right angle triangle, then what you will have, let's say like that, and you have your right angle, that side is already an altitude, okay, because of that right angle from the two sides. Okay. Let me, then I can remove that because the next one. So you need to put the ratio of those. So you're gonna have to make sure you have your shape, all right, like that. So you have your two altitudes that intersect here. What you do is looking at the angle. So the first one is CEA. So CEA is equal, it's a right angle. So CEA is equal to CFB, which is CFB. So it's that. So let me annotate that so you can see graphically. So let's say I do the red one. So that will be this side and that one. Okay. Then you have ACE and BCF. So that angle here is common to any triangles you try to build up. So here they chose ACE to be compliant with the first one, CEA. okay, and BCF is a rearrange. So now we have two angles that are going to be equal. So you can say that those two triangles, CAE and uh, CBF, so that one, so that triangle here with, I don't know, let's say this one, ACE, are similar, okay? So they have the same angle. Basically the green one, if you flip it around, it will match the orange triangle. So what you do is the ratio, you do the ratio of, so for CBF you use AE over BF is going to be equal, yes, to AC over BC, okay? So probably a good idea to actually also redraw the triangle in the correct side. So I would do something like this one. So let's say the dark one. I would let's say I leave AEC, okay, and then the other one I'll flip it around, so it's gonna be similar. So that end is still C, but I'm looking at B and F, and I will I have a right angle at F, so my F is going to be here and my B is going to be there. So what they do is, to get those ratio, AE will correspond to this side for the left hand side, alright? So that's for the left hand side of the equation, and the AC will represent this one. So when you do the 1 over equals to the 2, so you compare that side with that one, that side with that one, you end up with a correct ratio, okay? Alright, then you can have also a situation like it's a parallelogram, so you have ABCD, you have ABC being the acute angle. Again, it depends how you tilt your parallelogram. So in that situation, you want this angle to be acute and not the other one. I forgot the other term. Louis, what's the complementary or the supplementary of acute? Okay, I thought obtuse, but I thought I was wrong. Okay, sounds right. Okay, so BM is perpendicular to DC extended, and BN is perpendicular to DA extended. So again, you need to come up with a drawing. Once you come up with a drawing, you identify the two triangles you want to compare, look for a similarity property, and then you can write your ratios, and then when you rearrange your ratio, you should have a product like that. Okay? So notice when you do your drawing, so notice, well, first, the angle ABC is acute, so that's your angle ABC. Now, when you extend, notice that the points might be on the outside. Okay, so it does happen. It's going to be on the outside of your shape. So you have your outside shape, and then what you do is you're going to look at those two triangles. So the triangle N, I call it ABN, and BMC. So those are the two triangles you're going to look at, because what you're looking for is, on that side you have an NA, which is over here, and for the other triangles you have a CM. Okay, now do you know where does that DC and DA come from? Because for example, if I look at CM is in my triangle, but DC is not in any of those two triangles. So why is this doing here? And the same with DA. What is this doing here? Hang on. a diagonal. There's no other drawing. Now, Monish, why are we taking AB then?
Because it's in the same triangle as AN.
Okay. What? But this relationship has DC. There's no AB, so fine. You use AB, but how are you going to change it to using AD or DC then? I'm going to go back to the original question. On the first statement, it says there is a parallelogram. Now, with a parallelogram, what is particular about that shape? What are the it has some properties. Louis, you don't need to draw the diagonals. Anyone?
Got two pairs of parallel lines.
Okay, so they are the opposite sides are parallel. Yep.
Yeah.
Okay. Now, so you have those two sides. Well, I'm moving my mouse over. I have those two sides that are parallel. Is there anything else you can tell me about those sides that are parallel? Okay, the opposite angles are the same. Yeah, it adds up to 360. But by the way, that's for any quadrilateral.
Mister, is our aim to prove BAN and CMB similar?
No, I'm not there yet. I just want to talk about we're gonna need that later possibly, but at the moment what I want to do is, because on that relationship, that answer, I have DC and DA, but it's not what I'm after. I want AB. Because I'm gonna look at those two triangles here. Okay, so forget about the angles for a second, and I'm going back to that parallelogram. ABCD. I'm gonna state it, and I know for all of you it's gonna be obvious, unless Monish, you wanna throw that in? No?
What?
Okay. The opposite sides are parallel. You already stated that, but what's actually important is the opposite sides are also equal. So what it means is AB is also equal to DC. So that DC over here is also AB. And we're going to do the same with AD. So it's something that you need to keep in mind for to do that proofing. I think you were, probably I wasn't clear with the question. You went to the angles because you were looking at similarities. I wasn't there yet. I was just looking at the final statement that needed to be proven, is just how confusing you have these CD and AD. Okay?
Yeah.
Alright, so it's kind of, let me see. So you look at the alternate angle, so it would be nice if I moved that. I need the drawing as well. So you have your angle BCM, that angle, so BCM, that angle here is going to be equal to that angle ABC. They are alternate angles. How did it work out? Hang on, what am I doing? Okay. So that angle BCM is actually alternate with that angle. but that angle over here is also corresponding to ABC. That's the idea. It's because of those those lines being parallel. BAN, so BAN is that angle, okay? It can also be alternate with that angle there, meaning that it's going to be equal to that angle ABC. So you have all those angle equalities, you have that one as well, you have also the 90 degrees. So you end up with those two triangles to be similar. We can write the ratios of the length. Now that's coming from a parallelogram, okay? And you substitute AB and BC, so on that side, and you end up with that relationship in terms of M and N, and we can write it as a product, and this is what you need to prove, okay? Alright, so have a look back about the way they're looking at the angles. There's different ways that can be done, okay? There's not only one way to prove that those two triangles are similar, okay? Alright, so another situation. So you look at different shapes. It can be, we look at the parallelogram. We use the right angle triangle. In the situation with the trapezium, this time you're going to be using the diagonals. So trapezium, remember, it's a shape that has two parallel opposite sides, okay? So what you would have is the line through O parallel to the base CD. So I need a drawing. So you have your A, B, C, D here. The diagonals like that goes through O. You have a line that goes through O that needs to be parallel.
Parallel lines.
Yes, you have a question?
No.
Okay. That intersects at X. So looking at the triangle, so you need to prove that equality. Probably a good idea to write it as a ratio. So if you write it as a ratio, you have I would regroup, because what you want to do is, by regrouping as a ratio, the idea is you're not allowed to use the proofing, but it will guide you to go kind of backwards. So that equality of ratio is going to come from the ratios of similar triangles. So you need to find two similar triangles. You need to identify the three letters that make up those triangles, and then knowing those two triangles, then you're going to look at how you're going to prove that those two triangles are similar using any properties like AAA or triple S or SAS, okay? So here what I would do is either, so let me see, what options do I have? So I'm gonna group this one with this one, alright, and AB with that one, okay? So I have ABX, and that's not a triangle, so that's not a good idea, okay? Forget what I just did. So it's a little bit of trial and error, so we need a B, so it's going to be probably BX. But then again, no, they're parallels, but they're not necessarily equal. Alright, so what we do is, let's look at the triangles. So let's say I forget that. What you could do is that one is the same, so that's A, B, C. I'm just gonna go with this. So the way they're gonna look at, so they look at those two triangles, so all the angles are the same. So you look at the pair of parallel lines. So here I have two parallel lines, and here I have either that one, but I'm going to use that one in the middle. So that one combined with that one. So first, if I look at those two here, I'm gonna look at that triangle ABC. Alright. And that triangle has a common angle, this one, with the smaller triangle OX.
Miss,
Yes, Monish?
can you take away the white sheet?
That would help. Is that better?
Yes.
Yes.
Okay. So those two lines are parallel, AB and OX. So if I look at my triangle ABC, and because I have two parallel lines here, I'm going to have some corresponding angles. So that angle is corresponding with that one is corresponding with that one, and that angle in the corner is going to be common to both triangles. So then you can end up with this equality for ABC, that's a large triangle, okay? And OXC is the same corner C, and you're going to have that equality. Now, once you do that, you can write that ratio, okay? So we have that side. What did they use BX for? Hang on, no, I'm pointing to the wrong one, sorry. Hang on, I did it. OXC ABC. No, sorry, that's the wrong one. Because here it has CD, so it's the other side. So here, what I do, is you have ABC OXC. Yeah, it is the thank you. It's the second equation. So you have XC. So this line, we're gonna do the ratio with BC. So it's XC over BC. Okay, so the short one divided by the long one, and we can do that with from here. What you can use this side, but let's say we're gonna use the parallel line. So the short one is OX divided by AB. Okay, so they are the corresponding side of the two triangles. Okay, with the second one, which is DCB, that somewhere here. It's kind of weird. What's that? No? Weird how I can. So here what you would do is you have DCB and OXB, and that's coming from this side. So I would have DCB, and that line is parallel with that one. Okay, and that's B. B is in common. Okay, so the large triangle is DCB, so that's my triangle here, and the smaller one is OXB. And then we can write the ratio. So here they use B to go towards, so it's BX over BC is going to be equal to OX over DC. So you end up with two expressions with ratios, okay? And what you need to do by doing the division, what's happening is you simplify, you remove the terms that you don't need. So BC and OX cancel out, and you end up with that ratio. You do a cross product, and you end up with that product, which is what you need to prove. Isaac, I could have divided the long side by the short side. What it would have happened is those ratio will be the reciprocal, so you will have BC over BX. But at the end, because it's an equation, it doesn't matter if I, for example, if I say 1 over 2 is equal to 2 over 4, as an equation, it's the same as if I do the reciprocal. 2 over 1 is the same as 4 over 2. So it doesn't really matter which one did you pick. Do you pick the large length divided by the smaller one, or the vice versa? It doesn't really matter. As long as when you simplify your equation, you should fall back to your same answer. Okay? Alright. And that's it. That's 9G. 9F and 9G. Any questions before I move on with the year 12s?
No.